All right, okay. So just let's see, people are still joining. And now we can start. All right, okay. So let's start. So today's topic is going to be entropy regularized optimal transport. So once again, you guys can hear me clearly. Let me just check that the recording is being done. I think it should be. Okay, great. Good. So we're going to talk about this immensely important field of entropy regularized optimal transport. This is crucial because of current applications in statistics and machine learning, where the actual optimal transport usually cannot be computed very efficiently. And so people resort to these approximations, and one of the main approximations that people use is entropy regularized optimal transport, which not only has wonderful geometric properties, but also computationally it's much easier to handle. Um, in fact, it's so much popular that I heard this story that when you talk to people about optimal transport in machine learning, the only concept that they actually know is entropy regularized optimal transport, because it's just so widely used in actual applications. So I'll first start by writing down the definition of the problem. So as before, let P2 of RD these are all probability measures on RD with finite second moments. And I take mu and nu to be my two marginals. Nu in P2 of RD. These are my two fixed marginals. As always, my set of couplings, pi of mu and nu, this will be my set of couplings. Mu and nu. Now, if I take a coupling, which is, let's say, gamma, let's take a coupling gamma in pi of mu and nu, then one can consider the entropy of gamma. This is the integral of gamma x log of gamma x dx, if gamma is absolutely continuous with respect to Lebesgue, and this is infinity otherwise. Now, I want to make sure that you understand the difference of this setup, which is slightly different from what we've been doing before. Gamma is a probability distribution on RD cross RD. It's a coupling. And so when I say that gamma is absolutely continuous with respect to Lebesgue, I mean that I'm looking into couplings of mu and nu which have a joint density. Is that clear? If it does not have a joint density, then entropy is infinity. This is the case, for example, when gamma is the optimal Brunier coupling. The Brunier coupling is given by a Brunier map. Therefore, it doesn't have a joint density. Therefore, it is infinite entropy. So I'm not considering couplings like that. I'm only considering couplings of mu and nu that have a joint density. Again, this set is non-empty because if mu and nu themselves have density, then the product will have density. And in fact, I'm going to assume throughout this talk that they are absolutely continuous. Now, the EOT, so define entropy regularized OT cost as EOT epsilon, so for some epsilon positive, EOT epsilon mu nu to be the infimum over all couplings. The first term is just exactly as you would get from my Wasserstein cost. So y minus x norm square d gamma plus epsilon times the entropy of gamma. So what am I looking at? If it was just the Wasserstein, if it was just the Wasserstein 2 cost, then I would be looking into the first term. Now I've put as constant 1/2. Well, that's just for bookkeeping. You will see why this simplifies some of the stuff that I'm going to do later, but that's immaterial. I'm really minimizing the 1/2 integral of norm of 1 minus x norm squared. This is the thing that I would minimize if I'm doing just optimal transport. But I'm not doing just that. I'm kind of penalizing the coupling by its entropy by adding a term which is epsilon times entropy of gamma. You get this? So this is a different problem than the optimal transport problem. However, note, if epsilon is equal to 0, I get back 1/2 W2 square mu to nu. But I'm really interested in positive but small epsilon. Also, I would also remark that in practice, the squared cost is not what people usually talk about when doing this. You can do it for generalized for any cost function. To any cost C, you can correspondingly define infimum over gamma over couplings, integral of C, xy d gamma plus epsilon, entropy of gamma. And this would be my EOT cost for the cost function C. The entropy regularized thing for my cost function C. Good. Everyone is clear about this definition? Okay. Let me ask a question. How many of you have seen entropy regularized optimal transport this problem before? Have any of you seen this before? Okay. One of you has seen this. Okay, good. So as I'm saying, it is widely used in practice as a substitute for optimal transport itself, and we'll explore some of the reasons why this is true. But before that, again, note that EOT epsilon is minimizing a strictly convex objective function over the convex set phi. So here convexity is not geodesic convexity. This is just regular convexity. Now, when we were doing optimal transport, we say that, okay, this is a linear function that is being minimized over this convex set. And so this is linear programming. Now, when I'm doing my EOT thing, I'm doing my not linear, but this is linear. Entropy is actually convex in the usual, is strictly convex in the usual linear interpolation between measures. And so what I'm optimizing, I'm optimizing on, okay, it's strictly convex up to translation. But okay, beside that, I'm optimizing a strictly convex function over a set, the pi, where this set pi is convex. Now, from basic convex analysis, it's not hard to see that if I'm trying to minimize a strictly convex function over some nice convex set, it will have a unique minimum. It, of course, also is lower semi-continuous. So this is a lower semi-continuous, strictly convex function over the convex set phi. Hence, it admits a unique minimizer. This minimizer is what is called the Schrodinger bridge. So the minimizer of either of these problems, either this, the quadratic cost problem, or even the problem for the general cost function, sometimes it's called Schrodinger bridge, although historically it was a quadratic cost problem, which was called the Schrodinger bridge. This minimizer is called Schrodinger bridge after the famous physicist Schrodinger of the cat fame at temperature epsilon. Between mu and nu. Is this clear? So what is the EOT problem? The EOT problem is when you, instead of doing plain vanilla optimal transport, you penalize the coupling by its entropy, then you solve it. And then what is the Schrodinger bridge problem? The Schrodinger bridge is a solution, is a unique solution of the EOT problem. That's what is called a Schrodinger bridge. Again, let me go back to this point that the Brenier map, the coupling that you get, the optimal coupling that you get from Brenier map cannot be the solution, cannot be the Schrodinger bridge. Why? Because the solution to the Mosh-Kantorowicz problem is supported on the graph of the gradient of convex function, and therefore its entropy is infinity. So note that Schrodinger bridge I'm going to call this SB epsilon, has a joint density and it cannot be the solution of the Mosh-Kantorowicz problem as given by Brenier. Is this clear? Right? Entropy will blow up for the Brenier solution, so it cannot be. On the other hand, if I take epsilon equals to 0, as I've already noted, I get back my 1/2 Wasserstein 2 square. And so for epsilon equal to 0, I know that the Schrodinger bridge, the Schrodinger bridge is not quite well defined for epsilon equal to 0. It's only for epsilon positive. But for epsilon equal to 0, I get back my Brenier map. And so the natural question to ask is that as epsilon goes down to 0, can I recover my Brenier map from the limits of the Schrodinger bridges when epsilon is going down to 0? And that's really the crux of research here. However, one expects that as epsilon goes down to 0, the Schrodinger bridge will converge to the Mosh-Kantorowicz solution. And the research is all about, does it? How fast? That's really what we are going to study. Any questions? Do you guys understand what the problem is? Do you guys understand what I said, that what is the main thing to do here? I haven't talked about why people prefer Schrodinger bridge, but we're getting there because it's numerically you can compute it, statistically it's much nicer, it's much more robust and so on, but those we are coming. But this is the general problem. You replace a linear problem, linear optimization problem to a strictly convex optimization problem where the convexity is going to 0, and you hope to show that the solutions are converging.
And I understand it's sort of like a ridge and lasso regression compared to just ordinary least squares in that sense.
In what sense this is lasso regression?
Like our kind of this kind of regularization
Yes,
was for
so
similar
clearly,
purpose.
right. So the regularization does almost similar purpose. But yes, so in that sense, it is certainly similar to other such penalized optimization problems like, like lasso and so on. But this one has many, each one of the regularization you do for a very specific gain. So for sparsity, you do some regularization. For robustness, you do some regularization. So this particular regularization with entropy is done for computational and statistical robustness. But as we will see, it by itself is a very, very interesting mathematical object. But
Okay,
yes, it's similar in some sense. That's way.
Okay.
Okay.
So, sorry.
Yeah.
When epsilon is 0, the solution satisfies solves the Monte-Carlo problem.
Correct. Exactly.
But
epsilon equal to 0. Yes.
Right. And so now we want to see as epsilon decreases, does that does it converge to the same
exactly
thing? Okay.
Correct. Right. Correct. That's exactly what the problem is. All right. Okay. A little bit of historical reference here. So a little bit of history here. So the reason why this is called Schrodinger bridge problem is because in the 1930s, Aaron Schrodinger asked the following problem. Take a box. And imagine that the temperature is very cold. Very cold means very close to absolute 0. Not exactly 0, but very close to absolute 0. Temperature is epsilon, which is very close to 0, but it's still positive. Now you observe the box. The box has some gas molecules. You observe the box at 2 different time points, time t equals to 0 and time t equals to 1. So time t equals to 1. Now at time t equals to 0, imagine that the gas molecules are in this corner of the box with some shape. Now, as you know, that the temperature is really how much the molecules are vibrating. And so if the temperature is 0, in absolute 0, the molecules don't move at all. But if the temperature is close to 0, but not exactly 0, they will move a little bit, but you don't really expect them to move too much. And yet, suppose something very rare happens, and at time t equals to 1, you see the molecules in a very weird shape at the other corner. Okay, so this is a rare event in which, in spite of having a very small temperature, your molecules have changed their configuration, going from time t equals to 0 to time t equals to 1. And the question that Schrodinger asked is, what are the parts of these molecules? So the question that he asked what is the path followed by each molecule. As it changed configuration. Now you have to understand something about here, that the molecules are exchangeable. Like I cannot tell, I mean, there is no molecules that I can say, okay, this is a molecule that, like, I cannot identify them. So one of the molecules here has moved, let's say, there. One of the molecules here has, let's say, moved there. One of this molecule here could have moved there. Or some other matching. So if there are like 100 different molecules, there are all sorts of matchings between these molecules, they are possible. But only some of them are more likely than the others. As you can imagine, like, some cost more energy than the others. And so the question really can be boiled down to saying, okay, which matching is the best? And now if this molecule here is going to something over there, is it going to follow like a curvy path? Is it going to follow a straight path? Is it going to follow an almost straight path? What kind of path will it follow? Okay, that was the basic physics question that was asked by Erwin Schrödinger. Now, in 1980s, Hans Filmer gave a following description of the problem in terms of relative entropy. So Hans Filmer brought in relative entropy. So let me describe this. So let me describe this thing here. So let's go back to the EOT problem. Back to EOT. So my EOT problem between two marginals, EOT epsilon mu and nu, was this following problem. So I have the infimum over all couplings. I have 1/2 integral of y minus x norm square d gamma plus epsilon entropy of gamma. Now, what I'm going to do is that I'm going to create a sigma finite measure. So consider the following sigma finite measure. Which is r dx dy. This is dx, and then 1 over square root 2 pi epsilon to the power d over 2 e to the power minus y minus x norm square over 2 epsilon dy. Okay, what is this? Well, imagine that this box that we're seeing has infinite size. So over the box, everything is finite volume, everything is uniform, but imagine it's the entire space. The problem really doesn't change if it's the entire space. And so what these molecules, they are moving like Brownian motion. Okay. Now, if they're moving by Brownian motion, and if the temperature is epsilon, you can ask what is the transition density of the molecules from time 0 to time 1. And that's given by the Brownian transition density from time 0 to time epsilon. So this is my transition density of Brownian motion of a standard d-dimensional Brownian motion between time 0 and time epsilon. So I've kind of switched from time 0 to time 1 with temperature epsilon to time 0 to time epsilon, but this is what is called Brownian scaling. You can go back and forth between rescaling time and rescaling temperature. Yes, you have to trust me on this, that this is the right physical interpretation, that moving from time 0 to time 1 in temperature epsilon is the same as moving time 0 to time epsilon in temperature 1, which is what Brownian motion is doing. And so this is saying that the initial distribution is Lebesgue. is Lebesgue. So you start a position of a particle initially from the Lebesgue distribution, Lebesgue measure, and then you start a Brownian motion starting from that distribution, and you observe where that Brownian motion is after time epsilon, and that's a density which is the transition density times dy. And now you ask what is the joint distribution of the particle at time 0 and time epsilon, and that's R. So joint distribution, so I'd rather joint density, I should say density because it's not quite probability density, of a particle which is Brownian motion, performing Brownian motion, starting initially at Lebesgue measure and then moving like Brownian motion up to time epsilon. Right? That's a sigma finite measure. Now, if I take any gamma, for any gamma in the set of couplings, let's consider the Kullback-Leibler of gamma with respect to R. So I should call this R epsilon, so R epsilon. This is allowed. Although R epsilon is no longer a probability measure, this is still allowed. Gamma is a probability measure. This is still allowed. And I can write this from my formula for Kullback-Leibler. This is the integral of gamma xy log gamma xy divided by R epsilon xy dx dy. Now, we have done this calculation many, many times. If I'm doing Kullback-Leibler, then that breaks down into two pieces. The first part is entropy, and the second part is a linear term. So I would get exactly the same thing here. I would get that this is equal to the entropy of gamma. And then from here, I get this is 1 over 2 epsilon integral of y minus x norm square over 2 I don't need the 2 epsilon anymore. D gamma. And then plus some constant. D over 2 log 2 pi epsilon. So that's my Kullback-Leibler. And so look at this problem, which is the EOT problem here. Over all gamma couplings, I'm minimizing 1/2 y norm of y minus x square epsilon entropy of gamma. Instead, I could try to minimize epsilon times this Kullback-Leibler quantity, which will give me epsilon entropy of gamma plus 1/2 this, plus a constant that I don't care about. So if I'm trying to minimize gamma to epsilon Kullback-Leibler gamma with respect to R epsilon, then I would be minimizing 1/2 integral y minus x norm squared d gamma plus epsilon entropy of gamma and plus a constant that I don't care about because it doesn't enter the picture. So the problem of the EOT problem, where I take the point of view of penalizing my Moshkan-Turovich problem by entropy, is also equivalent to solve a Kullback-Leibler minimization problem, where I'm minimizing the Kullback-Leibler of any coupling from the natural transition of a symmetric Brownian motion. Okay. So the Schrodinger bridge epsilon is also the arg inf over gamma in the set of couplings, Kullback-Leibler gamma with respect to R epsilon. Okay. This is the observation that you make. Is this clear? So what I'm saying is that these two optimization problems are equivalent. In the first optimization problem, I take the point of view that I'm penalizing my Wasserstein 2 cost function by entropy. Okay, that's my first optimization problem. The second optimization problem, I'm saying I'm minimizing Kullback-Leibler of any coupling from the natural joint distribution that I get from Brownian motion. And because the two differ by a scaling and a constant, minimizing one is the same as minimizing the other. In particular, the minimizer is the same. And so the Schrodinger bridge is exactly the minimizer of the problem. Among the set of couplings, which one minimizes relative entropy or Kullback-Leibler from the natural motion of Brownian motion? Are you guys okay with this? All right, okay.
Okay.
Sorry, go ahead. All right, okay. So I get that this is a minimizer of this Kullback-Leibler. And now you may or may not know this, that this kind of Kullback-Leibler minimizations often come up in what is called conditioning. So you can think of conditioning as a Kullback-Leibler minimization. This is not a place where I can get into this, but try to do some kind of conditional distributions. Like take a probability measure, condition the probability measure on a certain set A, and try to write the conditional measure as a unique solution to a Kullback-Leibler minimization. You'll see what I'm saying. This is a common idea. And so the Schrodinger bridge can also be interpreted as, Brownian motion conditioned to have initial distribution mu and terminal distribution at time epsilon given by nu. Okay. This doesn't quite make sense. It's a bit formal because it doesn't quite make sense as a strict conditioning. When you condition a random variable, you condition on a random variable taking a certain values in certain set. That's not this kind of conditioning. It's some sort of distributional conditioning. But you make sense of it by this Kullback-Leibler projection. So if I have a Brownian motion, if it starts from nu, then its distribution at time epsilon is not going to be nu in general. It's going to be mu convoluted with the Gaussian transition density. But suppose I have a two-sided conditioning that a Brownian motion has distribution nu at time 0, distribution nu at time epsilon, and you ask what is the joint distribution of this Brownian motion? Well, that's a Schrodinger bridge, which is a solution of this Kullback-Leibler projection. Okay. So that's the second interpretation of this problem. Now, again, going to the history, sometime in like 2010 to 2015, kind of independently, both probabilists and machine learning people who are trying to use optimal transport, they got interested in Schrodinger bridge. Now, in 2013, there was a landmark paper that appeared in a machine learning journal, which is 2013. This is a paper by Marco Couturi, who showed that this Schrodinger bridge, this can be computed very efficiently for a discrete, purely atomic data by using an algorithm called the Synchron algorithm. The Schrodinger bridge can be computed efficiently, and it's some notion of efficiency, using the Synchron algorithm. And this kind of was the beginning of the explosion of interest from optimal transport in machine learning, mostly because now there's an algorithm to compute it. Now, what is the Synchron algorithm? We'll come to that. Synchron is a name of a person who gave rise to this algorithm that is called the Synchron algorithm in matrix algebra. In statistics, it is often called the IPFP algorithm for continuous densities. It is called iterated proportional fitting procedure. But nowadays, nobody really uses this name, and you can see why. IPFP makes no sense. Iterated proportional fitting procedure is a mouthful. Synchron is an attractive name. Everybody calls Synchron algorithm, whether you're using discrete or densities. But okay. So this paper, 2013, really the landmark paper because it kind of exploded this use of optimal transport in applications, and that's how people always use Synchron algorithm for applications. But Marco Couturi is not the first person to actually propose this algorithm to compute this approximation. There are other people who have done this before. We'll talk about some of them. In fact, the earliest person who mentioned this thing is this French mathematician called Forte, and this was done in 1940s. He also talked about using the Synchron type algorithm or IPFP to solve this problem. But since then, even in 2009, it has appeared even in economics literature by Galichon and Salani, around 09, and many other papers have actually used this. But Marco Couturi's paper was the one that introduced the machine learning community to this, and is the most famous one. All right, okay. So now let's go back to how does the Schrodinger bridge actually look like? Let's ask this question. So if I'm doing my optimal transport problem, I have Brunier's theorem, which tells me that the solution looks like the gradient of a convex function, and your solution is very degenerate and lives over that, the graph of this gradient of convex function. And one may ask the same question that for epsilon positive, how does Schrodinger bridge look like? Now, we know that it has a joint density. And so the question is really asking, can I somehow describe its joint density? Can it be arbitrary? Can it be something nice? And the theorem here this is from the 90s, Ruschendorf. Although it's built on earlier work of Zeiser from the 1960s, has the following theorem. That let gamma epsilon star be the density of the Schrodinger bridge. Then there exist potentials A epsilon and B epsilon such that one can write a gamma epsilon star xy divided by mu x, mu y, which are densities, as exponential minus 1 over 2 epsilon norm of y minus x square minus a epsilon of x over epsilon minus b epsilon of y over epsilon. Okay. Now, so what is this saying? It's saying that the joint density of the Schrodinger bridge cannot be arbitrary. It must look exactly of a particular form. And that particular form is that the first term of the joint density should be exactly what the Brownian transition density is, e to the power minus 1 over 2 epsilon y minus x norm square. And then there are some undetermined and mysterious potentials, A epsilon of x and B epsilon of y, such that gamma epsilon star, when you take the ratio over mu x times mu y, should look like this. Now, these terms A epsilon of x and B epsilon of y, which are called Schrodinger potentials, are uniquely determined by the marginal constraint. So what do I mean by marginal constraints? Well, I know that gamma epsilon star xy, if I integrate dy, I would get nu I. Why? Because gamma epsilon star is in the set of couplings. And so if I integrate this, I would get that this is equal to nu I. Then there's an integral which is e to the power minus 1 over 2 epsilon, norm of y minus x squared. Then there is minus b epsilon of y over epsilon. There is, sorry, I did something wrong here. Dy would give me mu x. So mu x would be the integral of gamma epsilon star when you integrate with respect to y. And so now if I integrate this, I would get this is mu x. This is nu y dy. And this is e to the power minus a epsilon of x over epsilon. Good, I'm just integrating this. But then if I cancel mu x from both sides, then I recover that a epsilon of x is equal to epsilon log integral e to the power minus 1 over 2 epsilon y minus x norm square minus b epsilon of y over epsilon nu y dy. Right? So it must satisfy this. Similarly, by flipping the role of x and y, I get that b epsilon of y must be equal to epsilon log integral e to the power minus 1 over 2 epsilon x minus y norm square minus a epsilon of x over epsilon mu of x dx. This system has to be satisfied. And the theorem is saying that there is a solution of this system. I can actually solve for these two functions, a epsilon and b epsilon, which satisfies these two equalities. And such a solution is the unique Schrodinger bridge that I get from solving my optimization problem. Are you guys okay with this? That's what the theorem is saying. Okay, so it cannot be arbitrary density. It must have a very particular form. It must be the only place where x and y interact must be through the Brownian transition density, norm of e to the power, norm of y minus x squared. The other two are just individual functions, but because it's in the set of couplings, it must satisfy this constraint that the two functions cannot be arbitrary. They must satisfy some kind of equation between the two. And this system is critical for understanding that. Any questions? Do you understand what the statement is? All right, okay. So the question is that, okay, how do I see this thing? Why is it that such a mysterious characterization theorem holds? And how can I expect that this should be true? So let's take some time for the rest of the class to understand what exactly is a Kullback-Leibler projection, because this concept of Kullback-Leibler projection also appears in many other contexts, and it's important to understand. It's important to develop a good sense of this. So let's leave this for a while to go back to Kullback-Leibler projections. How to solve KL projections. So I take a general approach here. So I'm working on probability measures on RD. I have some fixed probability measure, let's say R. So R is some probability measure. Let's say it has a density. So e to the power minus v is a density. And I take some gamma, some subset of these probability measures on RD. And I look into what is the arginf of little gamma and big gamma of Kullback-Leibler of gamma from R. So this is my set gamma. This is my probability measure R. I'm measuring distance by KL with respect to R, and I'm trying to find out the set that minimizes this distance. That's the idea of the projection. And so how does the projection look like? There's a problem that occurs very, very commonly in statistics, in physics, in probability, many, many areas. Let's try to understand this problem. Okay. Let's start with a simple example. So a very simple example of gamma. Take gamma to be all probability measures. Take gamma to be all probability measures little gamma, such that for some function f, I get f d gamma is equal to some constant alpha. Or so just alpha. So f is a fixed function. Alpha is a constant. Okay. It's a linear constraint. So I'm looking into, so for example, f could be the function, let's say x1. Alpha could be 0. And then I'm looking into all probability measures such that the mean of the first coordinate is 0. Are you with me? And so if I want to write down what is Kullback-Leibler of gamma, can we just switch from green? If I write down what is the Kullback-Leibler, of gamma with respect to R. So remember, R is e to the power minus v. So if I'm trying to minimize this with this one constraint, I can turn this to an unconstrained minimizer by introducing a Lagrange multiplier. So I'm going to do this infimum over gamma in gamma. So turn this to an unconstrained minimizing problem. By using a Lagrange multiplier. Okay, so what would I do then? I would take the full infimum. I would take the full infimum of gamma in the all probability measures on RD, and I would look into Kullback-Leibler of gamma with respect to R And then I would take, let's say, some lambda. This is my Lagrange multiplier. And I would take integral of f d gamma minus alpha. Makes sense? I can do this. So I can take a Lagrange multiplier, and I can do this, put this Lagrange multiplier and try to minimize this. Now this Kullback-Leibler, as always, I can break it into two parts. There's entropy plus a linear part. So recall that R is e to the power minus v. And so I can write this entire quantity as, okay, so this is arginf. I can write this entire quantity as arginf over gamma. This is entropy of gamma plus integral v d gamma plus integral lambda f d gamma. I can ignore the constant, it doesn't play a role here. I can join these two and say that this is the integral of v plus lambda f d gamma. So I'm back to the point of having entropy plus a linear function being minimized. And therefore, I can define R lambda to be a quantity which is e to the power minus v, e to the power minus lambda f. Okay, some quantity like this, e to the power minus v plus e to the power minus lambda f. And I will turn this to be a probability measure by multiplying by some c lambda. Okay. I just put this c lambda here. This is a probability density for some c lambda constant. So I'm looking into a density of the form e to the power minus v plus lambda f, and then some constant minus c lambda. Or you can, if you wish, you can think of it like e to the power minus lambda f minus c lambda, and I'm changing my measure, my original measure, which is r. So define this a measure like this. And then this problem now boils down to arginf of gamma, and now it becomes Kullback-Leibler of gamma with respect to r lambda. But I know exactly what the solution is. This is minimizing Kullback-Leibler, and the solution is, of course, r lambda itself. Okay, so let's go over this argument again. It's a very clever argument, and no step I'm doing anything very difficult, but it gives some very surprising answer. So what have I done here? I'm trying to solve a constrained optimization problem. I'm trying to solve a problem where I'm looking into take the minimum of the infimum of gamma with respect to r, where gamma is constrained to remain inside a set of all probability measures such that the integral of f d gamma is alpha, where f is given, alpha is given. I turn this to an unconstrained problem by introducing a Lagrange multiplier. So I say, okay, let's introduce some Lagrange multiplier lambda, and instead of putting myself in this set gamma, I have an unconstrained problem, and I take Kullback-Leibler gamma at r lambda integral of f d gamma minus alpha. And now I can write this Kullback-Leibler as entropy plus a linear function. Lambda f gives me another linear function, so I can combine the two, v plus lambda f. And so that gives me an idea that this is again entropy plus a linear function. And so I can combine the two and get back Kullback-Leibler. But this is Kullback-Leibler with respect to a different probability measure. What is that probability measure? It's e to the power minus lambda f minus some constant times the original r. And if I can find such a probability measure, then this becomes arginf of Kullback-Leibler with respect to this probability measure. And such a probability measure is actually going to be, the minimum of the Kullback-Leibler is going to be r lambda. So where is the Lagrange multiplier constraint being put? the Lagrange multiplier constraint is being put in the constraint that if I can find lambda such that integral of f d r lambda is exactly equal to alpha, then such an r lambda must be arginf over gamma Kullback-Leibler gamma with respect to r. That's a conclusion. Okay. So the question is, can I find a lambda such that if I change the measure r by e to the power minus lambda f, then integral of f dr lambda is equal to alpha. If I can do this, then that's a solution. How are you guys feeling about this? Have you seen this argument before? Okay. Let's see an example. So let's see, here's an example. Solve the following entropy minimization problem, which is arginf over gamma, entropy of gamma over all the set. So let's say gamma, this is the set of all probability measures such that the integral of norm x squared d gamma is equal to 1. Okay, and then look into this, arginf of entropy of gamma. All right, okay, so look into this problem. So can I solve for the minimum entropy distribution whose the second moment is exactly equal to 1? Do you know what the solution is? Okay, so gamma in gamma. Does anybody know what the solution is? Anybody care to guess?
I think that's just normal.
So, yeah, so I should say take d equals to 1. Correct. The solution is normal. Actually, this is very well known that the solution is normal. And how does the solution look like? The solution look like gamma x is like e to the power minus mod x squared over 2. And then, okay, you have, let's say, 1 over square root 2 pi. And that's a density. So where am I getting this quantity minus mod x squared over 2? Is the same function over which I built the constraint. What is the v that I'm minimizing this over? What is the r? That's just Lebesgue. So r is here Lebesgue. And so this argument is saying that the normal is the unique minimizer, because the way I'm getting my normal is I'm looking at this potential, which is e to the power minus x squared. The constant lambda is 1/2 here. The constant c lambda is whatever you get, this log of 1 over square root 2 pi. And because I can find these constants, which satisfies that this norm x squared d gamma is equal to 1, which is the case for standard normal, therefore this must be the infimum of this entropy. Good. And so from here, people, for example, get this very useful corollary that if you have gamma is any probability distribution such that the integral of mod x squared d gamma is equal to 1, then I must have that the entropy of gamma is greater than or equal to the entropy of normal 0, 1, which you can compute. This is, I forget the formula for this, but you can exactly compute what this entropy for normal 0, 1 is. Okay. And so this is often very, very useful to find bounds on entropy given certain moments. And now you know from here how to compute this. Okay, what happened here? Do you understand this method? Okay, do you guys understand this method? Let's go back to a more complicated example where now we have multiple linear constraints. So here's example 2. Suppose there's a bunch of functions. Suppose there are functions f1, f2, up to fk. These are given functions. And constants, which are alpha 1, alpha 2, up to alpha k. These are constants, so functions. Constants. And my set gamma is given by all probability measures little gamma, such that the integral of fi d gamma is equal to alpha I, for I is equal to 1 to up to k. So let's say mean is 0, variance is 1, fourth moment is 4, something like this. Okay, so this, I'm assuming gamma is non-empty. Okay, this may not be always feasible, but let's assume that is gamma is non-empty. Same deal. I take my R to be of the form e to the power minus v, and I'm looking for what is the arginf of gamma in capital gamma of Kullback-Leibler of gamma with respect to R. Good. How do I solve this? Exactly the same way. There are k-many constraints to introduce k-many Lagrange multipliers, and you turn this problem to an unconstrained problem. Which is that you look into arginf over all gamma, not necessarily inside the set capital gamma, and you look into what is Kullback-Leibler gamma with respect to R, and then you add these things. So lambda I fi minus alpha I for I equals to 1 to k. What is the solution for this? The solution for this will look like some density R lambda, where lambda is now a vector, lambda 1 to lambda k of x, which would be of the type which is e to the power minus summation lambda I fi of x for I equals to 1 to k minus some constant c lambda multiplying the original probability measure mu, or r, sorry, not mu, but r. R. If you can find lambda i's, lambda 1 to lambda k, such that integral of every fi with respect to r lambda, this is given by alpha I, for I is equal to 1, 2, 3 up to k, then this is a unique minimizer of the problem. Then such an r lambda is exactly the arginf of Kullback-Leibler over the set gamma of gamma with respect to r. Okay, so the solution always looks like this. You take the function over which you're putting the constraint, and then you're trying to find the Lagrange multipliers such that you're in the feasible set, and then the density that you get from this is the solution. Are you guys okay? Okay, so now let's go back to the problem that we started, which is the problem of taking a Kullback-Leibler projection on a set of couplings. So back to Schrodinger bridge. So my R epsilon xy for the Schrodinger bridge problem is given by, so recall, this is given by e to the power minus 1 over 2 epsilon I minus x norm square. That's what I'm trying to project down. The set gamma, this is pi of mu and nu, is a set of couplings of mu and nu. My first claim is that this set pi can be seen as a limit of sets with linear constraint. Okay, now I want you to answer this. Why is this true? Why is it that the set of couplings can be seen as a limit of the set that we were dealing with just before, which is that you can choose some functions and you can look into the integral of the functions and say these functions are equal to some values. Why can I think of the set of couplings as a limit of such sets? Or an intersection of a sequence of such sets? What is really the constraint on the set of couplings?
Just the marginal constraints.
Right, so the marginal constraint. So the x marginal is mu, y marginal is nu. Can I capture the marginal constraints by some, let's say, countable set of functional integrals?
Yes. Yeah.
Yes. Do you have a candidate in mind? So one possible candidate, for example, could be moments. If the measure is determined by the moments, I can say that the countable collection of x moments, so x squared, x cubed, x4, these moments are given by the moments of mu. And the countable collection of y moments are given by the moments of nu. This is one possibility. Or it could be some other kind of set, some other countable collection of functions that determine what the measure mu is. How do I know such a countable collection always exists? Because of separability. The set of Rd is separable. One can determine a measure by a countable collection of integrals. Does this make sense? So I can pick a countable collection of functions. So I can pick, due to separability, a countable family of functions Fk, k in n, such that the marginal constraint may be represented as that I look into Fk of x, then gamma xy, dx dy, and that's equal to Fk of x mu dx for all k. And that Fk of y gamma xy dx, oh, sorry, yeah, exactly. Dx dy this would be equal to integral of fk of y nu dy for all k. And the set fk has to be chosen in such a way which is called a distributional determining class. So it's a set of functions whose integrals determine a probability distribution. Why does such a class exist? Separability. Is this convincing? So given such a class of functions fk, the linear functions that I'm picking are twice as large. One is fk applied to the x coordinate, one is fk applied to the y coordinates. And then I integrate with respect to gamma. These are my constants. These are my constants alpha k and beta k. These are my constants. And these are my integrals, my linear integrals. Do you understand this? Okay. And so from my basic understanding of Kullback-Leibler projection, I get that if I can find gamma star, xy, which is of the following form, that gamma star xy which is like e to the power minus 1 over 2 epsilon y minus x norm square. Well, that comes from what I'm projecting. And then I have a bunch of these Lagrange multipliers. So I have a bunch of Lagrange multipliers. So k equals to 1 to infinity, let's say lambda k x, fkx, minus k equals to 1 to infinity, lambda k y, fky, such that, so of the form, such that gamma star is in the set of couplings, then gamma star must be the Schrödinger bridge. But this is just a function of x. So I can combine all of this and write a function phi of x. This is just a function of y. I can combine all of these and write it as a function of y. I can divide by epsilon and multiply by epsilon. Multiply by epsilon, divide by epsilon, multiply by epsilon. And then it goes back to the search of these potentials that I was looking for. So the gamma star xy is equal to mu x times nu I e to the power minus 1 over 2 epsilon y minus x norm square minus a epsilon of x over epsilon minus b epsilon of y over epsilon. I can write it in this way. So if I can find a epsilon and b epsilon such that gamma star is in the set of couplings, look what I've done is that I've multiplied by mu x times nu I. It doesn't make any difference. This just goes back to like rewriting the a epsilon and b epsilon suitably. That's not the problem. The point is that the only point of interaction is coming from the Brownian transition, which is y minus x norm square. So then the next part of the question is, how can I guarantee such an a epsilon, b epsilon exists? And this beautiful argument, which I will present next time, is that you can actually use the Synchron algorithm to say that a epsilon and b epsilon exist. This is the argument due to Forte, which uses convergence of Synchron algorithm. So I will talk about it next time. Let me just see what's the idea here. This is the argument by Forte. So if you go back to this point here, there's this ugly line which I will erase later. So look at this a epsilon and b epsilon. They have to satisfy some equation between the two. A epsilon, b epsilon are free. They have to satisfy some equation between the two. So one can think of A epsilon and B epsilon as a solution of a fixed point equation. It must satisfy some fixed point equation. There is B epsilon, which is here. B epsilon, you plug that back in, you get an equation on A epsilon on both sides, like on left and the right. And the solution of a fixed point equation, as you may know, can often be found by an iterative scheme. That iterative scheme, the natural iterative scheme, is precisely what the synchron algorithm is. And Forte showed that this iterative scheme converges. And when it converges, it gives me a solution of the fixed point equation. And that solves the original problem that, okay, there does exist such an A epsilon and B epsilon, which is in the set of couplings. And that's a solution of the synchron of the Schrodinger bridge problem. There are many other ways of proving this. Ruschendorf's proof is different. I really like Forte's proof because it uses a synchron algorithm. Okay, I'll stop here, but do you guys have any questions? Okay, so if not, have a good weekend and I'll see you guys on Monday.
Thank you.
You.